This problem, we're going to be exploring the concept of a titration curve. And so I have a couple different volumes that I'm going to run through. But basically what I'm going to be asking is for you to determine the pH of this solution when you have a certain volume of this strong base sodium hydroxide added to the weak acid of HF. I'm telling you it's a weak acid because one, I know it is. And additionally, I'm given a Ka value that is times 10 to the negative 4. So it's also further justifying the fact that this is actually a real weak acid. And so when we have 0 milliliters of this sodium hydroxide added to 50 milliliters of our 0.5 molarity HF, we know the only thing that's in there initially is just going to be our acid. And so because we're given that molarity and we're given volume, we can solve it one way or another. And also the fact we're given Ka, we can solve for the pH and everything else that way as well. And so there's a couple different routes. The route that I went is just to kind of keep my life very simple and non-complicated. Is if we know the Ka is the concentration of our H3O plus, F minus, and HF, and we know the Ka. We also know the concentration of our HF because it's given to us. And so here we know that the Ka is going to be x squared because using all of our previous knowledge, we know that not very much of this HF is going to decompose, but whatever amount of HF breaks down, it's going to produce 1 mole of H3O plus and 1 mole of F minus, and it's going to be the same concentrations for the both of these. So replacing your H3O plus and your F minus with X, you end up with X squared. Here on the bottom we have our HF because it's the reactant. Remember, water is thrown out because we're treating it as a pure substance that will not change its concentration. And so luckily for us, we know our Ka value right there. We know our concentration of our HF, and so we just need to plug these values in. And so solving, again, all I'm doing, going from this step to this step, is I am just moving our x squared over there and our Ka with our HF, and then taking the square root of both of those. So here, plug and chug, we can solve for the Ka and the HF, solve for x. We end up with 0.182 equals the concentration of our H3O plus. It also equals the concentration of F minus, but we'll talk about that later. And so now that we know the concentration of our H3O plus, we're trying to look for our pH. And so from there, we can solve for the pH is equal to the negative log of our hydronium concentration, or 1.74. And so this 1.74 is the concentration of your solution before any sodium hydroxide has been added, or it's the concentration of our HF by itself. And so the next step we're going to look at is what happens when we have added 25 milliliters of our sodium hydroxide. And so hopefully you should understand our pH should be going up because we're adding sodium hydroxide to an acid, or we're basically neutralizing this stuff. And so whatever amount of your HF that does decompose, that some of that H plus or the hydronium ions are going to react with that hydroxide. And so in this situation, we only have one choice that we can actually use, and we have to make up a rice table. Before we make up our rice table, we have to understand that we need to know what to plug into these values. So with the information given to us, we know we have 50 milliliters of our 0.5 moles or molarity HF. So using that information, we know that we have 0.025 moles of HF inside of our solution. And the fact that we have 25 milliliters of 0.5 molarity sodium hydroxide, we can use that information to calculate that we have 0.0125 moles of our hydroxide ions in our solution. And so right now, I'm going to keep everything in terms of moles, solve for moles, and then calculate molarity later on. If you want to right now, before you kind of plug this stuff into the rice table, convert these moles into molarity, that's perfectly fine. The one thing you have to remember and understand is that this moles cannot be thrown over 50 milliliters anymore. This moles cannot be thrown over 25 milliliters anymore, because both of these moles are now floating around in 75 milliliters of solution, because we have our 50 milliliters of our acid and 25 milliliters of our base. And so once you solve for these moles, you can go back and solve for concentration. But remember, you cannot use this 0.5 and that 0.5 anymore, because that's not actually the concentration anymore. So to keep things kind of simple, I'm going to keep everything in terms of moles in my rice table for now, and then convert from moles into molarity at the end whenever I know divide all of them by 75 milliliters. But again, doesn't matter how you go about it, as long as you keep everything straight and keep everything common with all your units and not convert some and don't convert the other. Just keep your life, again, on the right path, you'll be okay. And so, using the information given, we can write out the fact that I have an acid, and we're adding a base, and acid plus base will produce water and this conjugate acid. And so here, water is pure, leave it out of the whole ordeal. And we know 0.025 moles is going to be our concentration of our HF. We know 0.0125 moles is going to be the concentration of our hydroxide. Before any of this is mixed, you have a concentration of 0 of your conjugate base here. And so once we kind of go through and actually look at how these things are going to change, we know all of this hydroxide is going to react with some of this HF to produce some of our F minus. And again, all of the OH minus is going to react. So minus 1.25 hydroxide is going to be the same as minus 1.25 this HF, because this 0.125 moles of hydroxide is going to react with exactly 0.125 moles of this HF to produce exactly 0.125 moles of this F minus. And so when we kind of look at the initial and the change at equilibrium, our HF is going to have a new concentration of 0.0125. Our F minus is going to have a new concentration of 0.0125, and all of our OH minus is gone because all of it's reacted. And so, as I stated, this is in moles and moles and moles. You can still use the relationship of moles in all these equations, but in order to kind of keep things straight and not lie to you too much, I'm going to convert my moles into the concentrations in order to keep molarities all in the aspect here. And so just to be on the safe side, when you work through these problems, moles will typically work out to your advantage. You can still use moles instead of molarities when you plug them into these equations, but that one time that it doesn't work is going to be the one time that you're not going to notice, and it's going to cost you points. So just to be on the safe side, I'm going to convert my moles into molarity and use molarities for all my pH and pKa's and all those other calculations. But again, if you notice this, if you kind of go through, because these are the same values, they're going to be the same molarity. So molarity, moles, it's not going to make that big of a difference. But once I know the molarities of my HF and as of my F minus, I can use this fancy looking equation of pH equals pKa plus the log of our F minus over HF. In this case, the pKa is going to be the log of negative log of our Ka value that's given to you in the problem. The log of our F minus, we figure out the concentration of our F minus is 0.167. We know that the concentration of our HF is 0.167. And so here, one thing you should kind of notice is I'm taking the log of 1, and so that kind of just cancels itself out. And so you're really just looking at the negative log of this 6.6 times 10 to the negative 4 to give you a pH of 3.18. So, as I mentioned more than a couple times by now, there are multiple routes to go to get to this answer. Another route you could use, because say you didn't think about this equation, is to go about it the other way that we've been kind of looking at it and using the Ka equation. And so we know Ka equals your the concentration of your F minus times the concentration of your H3O plus divided by the concentration of your HF. So rearranging that equation, you know the concentration of your hydronium ion can equal Ka times HF divided by your F minus. We know Ka, we solve for HF, we solve for our F minus, and so if you solve for this, it ends up with 6.6 times 10 to the negative 4. But as we've done multiple times, if we have our hydronium ion, we can solve for pH by taking the pH equals negative log of your hydronium concentration, or negative log of 6.6 times 10 to the negative 4, which happens to equal 3.18. 3.18, same number, just different ways of going about it. So, the third aspect we have to look at is once we have added 50 milliliters of sodium hydroxide to our solution. And so at this point, one thing you should kind of, again, notice when we start going through and doing some of this math is if you convert both of these volumes and molarities into moles, you have 50 milliliters of 0.5 molarity HF is 0.025 moles of HF. And 50 milliliters of 0.5 molarity sodium hydroxide is 0.025 moles of sodium hydroxide. So in this case, we are looking at 0.25 moles of HF, 0.25 moles of hydroxide ions, or an equal amount of your H3O pluses and your OH minuses. We call this the equivalence point. In addition to that, we know at the equivalence point, 1 mole of HF plus 1 mole of hydroxide will give us 1 mole of our F minus. Or we also know that 0.025 moles of our acid plus 0.025 moles of our hydroxide will produce 0.025 moles of our F minus. And so here, if we kind of go through and look at this, we now know the moles of all of our products. If we know the moles, we can solve for the molarity. But as I mentioned before, you need to remember that we are looking at a total of 50 milliliters of acid plus 50 milliliters of sodium hydroxide. We're looking at 100 milliliters now instead of the individual solutions by themselves. And so in order to calculate the concentration, luckily for us in this case, they're all the same exact equation. And so the concentration of HF is equal to the concentration of our hydroxide is equal to the concentration of our F minus, or 0.025 divided by the total volume of our solution to get 0.25 molarity. And so now we know the concentrations of all of these things. In addition to that, we are given Ka. And so one thing we have to kind of notice here is at equilibrium, we're basically kind of looking at a little bit of, water, but we're looking at something that's not exactly going to be at a pH of 7. And the reason for that is because we are mixing a weak acid with a strong base. The only time you'll end up with a perfect neutralization and a pH of 7, like neutral, is if you're mixing a strong acid and strong base. And so here we can actually take advantage of the fact that we are creating a lot of water though. And so we can use the Kw, or 10 to the negative 14, or Ka, which is given to you as 6.6 times 10 to the negative 4, to solve for the Kb is 1.5 times 10 to the negative 11. And the reason why we did that is because we can use this crazy looking equation. Please check out the book and the videos that I've kind of posted in order to kind of go through and figure out how this equation comes about. But for now, just write it down, keep it in the back of your memory, put it on a post-it on your computer. But H3O plus, the concentration of your hydronium ions, is equal to Kw over Kb times the concentration of your conjugate base. And so here, we know the Kw is never going to change. It's going to be 10 to the negative 14. We just saw for our Kb is 1.5 times 10 to the negative 11. We saw for our F minus is 0.25. And so our hydronium concentration is 5.2 times 10 to the negative 9. And so, same deal as before. Once we know the hydronium ions, we can easily calculate the pH by negative log of the hydronium concentration of 5.2 times 10 to the negative 9 gives us a pH of 8.29. So as I mentioned before, this pH is not going to be 7 because you are not mixing a strong acid and strong base.